Welcome to our comprehensive guide on field effect transistors or FETs. In this unit, we'll explore the fascinating world of FETs, focusing on their construction, operation, and unique characteristics. FETs are essential components in modern electronics, widely used for their high input impedance and efficient switching capabilities. Whether you're a student, hobbyist, or professional, understanding FETs will deepen your knowledge of electronic circuit. Let's start by looking at what makes FETs different from other transistors and why they're so important in today's technology landscape. Field effect transistor or FET is a type of transistor that uses an electric field to control the flow of current. Unlike bipolar junction transistors (BJTs), which are controlled by current, FETs are voltage-controlled devices. This fundamental difference gives FETs several advantages, such as high input impedance and low power consumption. FETs are commonly found in amplifiers, switches, and digital circuits. In this video, we'll focus on two main types: the junction field effect transistor (JFET) and the metal oxide semiconductor FET (MOSFET). Let's begin with the junction field effect transistor or JFET. The JFET is constructed using a semiconductor channel, which can be either N-type or P-type. Two terminals called the source and drain are connected to either end of the channel. A third terminal known as the gate is placed adjacent to the channel and is separated by a reverse bias p-n junction. This unique structure allows the gate voltage to control the current flowing from source to drain. The simplicity of the JFET's construction makes it a popular choice for many analog applications. Operation of a JFET is based on controlling the width of the channel through which current flows. When a voltage is applied between the source and drain, current flows through the channel. By applying a reverse voltage to the gate, the channel narrows, restricting current flow. The more negative the gate voltage, the less current can pass through. This voltage-controlled behavior is what makes the JFET so useful in amplifying and switching applications. The JFET operates in three regions: ohmic, active, and cutoff. Symbol for a JFET clearly shows its three terminals: source, drain, and gate. The arrow on the gate indicates the direction of conventional current flow for N-channel or P-channel devices. Understanding the symbol is crucial for reading circuit diagrams and designing electronic circuits. The source is where carriers enter, the drain is where they exit, and the gate controls the channel between them. This simple yet effective design is the foundation of many analog circuits. Transfer characteristics of a JFET describe how the drain current changes with varying gate source voltage. Typically, as the gate source voltage becomes more negative, the drain current decreases. This relationship is often represented by a parabolic curve on a graph. The transfer characteristic is essential for understanding how the JFET amplifies signals and how it can be biased for different applications. By analyzing this curve, engineers can predict the behavior of the JFET in various circuits. Output characteristics of a JFET show how the drain current varies with the drain source voltage for different gate source voltages. These curves help us understand the different regions of operation: ohmic, active, and cutoff. In the ohmic region, the JFET behaves like a resistor. In the active region, it acts as a constant current source. In the cutoff region, the current is nearly zero. These characteristics are vital for designing amplifiers and switches using JFET. Fully understand JFETs, it's important to know their key parameters: transconductance (GM), drain resistance (ARD), and amplification factor (mu). Transconductance measures how effectively the gate voltage controls the drain current. Drain resistance indicates the resistance between the drain and source in the active region. The amplification factor is the product of transconductance and drain resistance, showing the overall gain capability of the JFET. These parameters help engineers select the right JFET for specific applications. Transconductance, symbolized as GM, is a crucial parameter for JFETs. It defines how much the drain current changes in response to a change in gate source voltage. A higher GM means the device is more sensitive to input voltage changes, making it ideal for amplification. Engineers use GM to determine the gain and efficiency of amplifiers built with JFETs. Understanding transconductance helps in designing circuits that require precise control of current flow. Drain resistance, denoted as ARD, represents the resistance between the drain and source terminals when the JFET is operating in the active region. A high drain resistance means the JFET can maintain a stable current even with changes in voltage. This property is especially useful in current source applications. Knowing the drain resistance helps engineers design circuits that require consistent current flow, such as analog signal processing. Amplification factor, symbolized as mu, is the product of transconductance and drain resistance. It indicates the overall gain capability of the JFET. A higher amplification factor means the device can provide greater signal amplification. This parameter is essential when designing high-gain amplifiers or sensitive signal detection circuits. By understanding mu, engineers can select the right JFET for applications that demand high performance. Biasing is the process of setting up the correct operating point for a JFET in a circuit. Proper biasing ensures that the JFET operates in the desired region, typically the active region for amplification. There are several methods for biasing a JFET, including self-bias, voltage divider bias, and source bias. Each method has its own advantages and is chosen based on the application requirements. Correct biasing is crucial for stable and predictable circuit performance. Self-bias method is one of the most common ways to bias a JFET. In this setup, a resistor is placed in the source lead, creating a voltage drop that automatically sets the gate source voltage. This method is simple, reliable, and widely used in amplifier circuits. The self-bias method helps maintain a stable operating point even if there are variations in device parameters, making it ideal for practical circuit design. Voltage divider bias uses two resistors to create a stable voltage at the gate terminal. This method provides better control over the gate voltage and is often used when precise biasing is required. By adjusting the resistor values, engineers can fine-tune the operating point of the JFET. Voltage divider bias is especially useful in circuits where consistent performance is critical, such as precision amplifiers. Source bias method involves applying a fixed voltage to the source terminal, while the gate is grounded. This creates a constant gate source voltage, ensuring the JFET operates in the desired region. Source bias is less common than self-bias or voltage divider bias, but can be useful in specific applications where a fixed bias is needed. Understanding different biasing methods allows engineers to choose the best approach for their circuit design. Now let's move on to another important type of FET, the metal oxide semiconductor field effect transistor or MOSFET. MOSFETs are widely used in both analog and digital circuits due to their high input impedance and fast switching speed. They come in two main types, enhancement mode and depletion mode. Understanding the structure and operation of MOSFETs is essential for anyone working with modern electronic devices. MOSFET consists of a source, drain gate, and a substrate. The gate is separated from the channel by a thin layer of insulating material, usually silicon dioxide. This structure allows the gate to control the channel without direct electrical contact, resulting in extremely high input impedance. The substrate can be either N-type or P-type, depending on the MOSFET type. This unique construction is what sets MOSFETs apart from other transistors. Enhancement mode MOSFETs are the most common type used in digital circuits. In this device, the channel does not exist naturally. When a voltage is applied to the gate, it creates an electric field that forms a conductive channel between the source and drain. The more positive the gate voltage, the more current can flow. Enhancement mode MOSFETs are ideal for switching applications due to their fast response and low power consumption. Depletion mode MOSFETs have a channel that exists even when no voltage is applied to the gate. Applying a negative gate voltage depletes the channel, reducing current flow. Conversely, a positive gate voltage enhances the channel, increasing current. Depletion mode MOSFETs are versatile and can be used in both analog and digital circuits. Their ability to operate with or without gate voltage makes them unique among FETs. Symbol for a MOSFET includes the source, drain, gate, and substrate terminals. The gate is shown separated from the channel by a line representing the insulating layer. The direction of the arrow indicates whether the device is N-channel or P-channel. Understanding the MOSFET symbol is essential for circuit design and analysis, as it helps identify the type and function of the device in a schematic. Transfer characteristics of a MOSFET describe how the drain current changes with varying gate source voltage. For enhancement mode devices, the drain current increases rapidly once the gate voltage exceeds a certain threshold. For depletion mode devices, the current can be controlled in both directions by adjusting the gate voltage. These characteristics are crucial for designing amplifiers and switches using MOSFET. Output characteristics of a MOSFET show how the drain current varies with the drain source voltage for different gate voltages. These curves help identify the device's operating regions, ohmic, saturation, and cutoff. In the ohmic region, the MOSFET behaves like a resistor. In saturation, it acts as a constant current source. Understanding these characteristics is essential for designing efficient electronic circuits. Icing a MOSFET involves setting the correct gate source voltage to ensure the device operates in the desired region. Proper biasing is crucial for stable operation, especially in amplifier circuits. Common biasing methods include voltage divider bias and source bias. Each method offers different levels of control and stability, and the choice depends on the specific application requirements. Enhancement and depletion mode MOSFETs differ in how they conduct current. Enhancement mode devices require a positive gate voltage to form a channel, while depletion mode devices have a channel by default and can be controlled by both positive and negative gate voltages. This distinction affects how each type is used in circuits, with enhancement mode being more common in digital applications and depletion mode in analog circuits. Let's compare bipolar junction transistors, BJTs, and junction field effect transistors, JFETs. BJTs are current-controlled devices while JFETs are voltage-controlled. BJTs typically have lower input impedance but higher gain, making them suitable for high-frequency applications. JFETs, on the other hand, offer high input impedance and are less noisy, making them ideal for sensitive analog circuits. Understanding these differences helps in selecting the right transistor for your project. FETs and MOSFETs are both types of FETs, but they have key differences. JFETs use a PN junction to control current, while MOSFETs use an insulated gate. MOSFETs offer higher input impedance and faster switching speeds, making them more suitable for digital circuits. JFETs are preferred in low-noise analog applications. Knowing these distinctions is important for choosing the best device for your circuit. BJTs and MOSFETs are both widely used transistors, but they operate differently. BJTs are current-controlled and can handle higher currents, making them suitable for power amplification. MOSFETs are voltage-controlled, have higher input impedance, and are more efficient in switching applications. Each type has its strengths and is chosen based on the specific needs of the circuit. FETs offer several advantages over BJTs, including high input impedance, low power consumption, and excellent thermal stability. These features make FETs ideal for use in integrated circuits, low-noise amplifiers, and switching devices. Their voltage-controlled operation also simplifies circuit design and reduces the risk of signal distortion. Despite their many advantages, FETs also have some drawbacks. They are more sensitive to static electricity and can be damaged by high voltages. FETs generally have lower gain compared to BJTs and may not be suitable for all high-frequency applications. Understanding these limitations is important when designing circuits that require robust performance. JFETs are widely used in analog circuits such as amplifiers, oscillators, and voltage-controlled resistors. Their high input impedance and low noise make them ideal for sensitive signal processing applications. JFETs are also found in audio equipment, test instruments, and radio frequency circuits, where signal integrity is crucial. MOSFETs are the backbone of modern digital electronics. They are used in microprocessors, memory devices, power supplies, and switching regulators. Their fast switching speed and high efficiency make them indispensable in computers, smartphones, and other digital devices. MOSFETs are also used in audio amplifiers and motor control circuits. FETs, especially MOSFETs, are the primary components in integrated circuits (ICs). Their small size, low power consumption, and high density make them ideal for large-scale integration. Modern microchips contain millions or even billions of MOSFETs, enabling the complex functionality of today's electronic devices. FETs are commonly used as electronic switches in both analog and digital circuits. Their fast switching speed and low on resistance make them ideal for controlling power to various parts of a circuit. FET switches are found in everything from power supplies to digital logic gates, providing efficient and reliable operation. FETs are widely used in amplifier circuits due to their high input impedance and low noise. They are ideal for preamplifiers, audio amplifiers, and radio frequency amplifiers. FET amplifiers provide clean, distortion-free signal amplification, making them essential in high-fidelity audio and communication systems. In analog circuits, FETs are used for signal amplification, filtering, and voltage regulation. Their ability to operate with minimal current makes them suitable for battery-powered devices and portable electronics. FETs help maintain signal integrity and reduce power consumption in a wide range of analog applications. FETs, particularly MOSFETs, are the foundation of digital logic circuits. They are used in logic gates, flip-flops, and memory cells. Their fast switching and low power requirements enable the high-speed operation of computers and digital systems. Without FETs, modern digital technology would not be possible. Power MOSFETs are used in power electronics for switching and amplification at high voltages and currents. They are found in power supplies, motor controllers, and inverters. Their efficiency and reliability make them the preferred choice for managing power in industrial and consumer electronics. FETs are known for their excellent thermal stability. Unlike BJTs, which can suffer from thermal runaway, FETs tend to self-regulate as temperature increases. This property makes them more reliable in environments where temperature fluctuations are common, such as automotive and industrial applications. FETs, especially JFETs, are prized for their low noise performance. This makes them ideal for use in sensitive analog circuits such as audio preamplifiers and measurement equipment. Low noise ensures that weak signals are amplified without introducing unwanted interference or distortion. FETs are commonly used in radio frequency (RF) circuits due to their high input impedance and fast response. They are found in RF amplifiers, mixers, and oscillators. Their ability to handle high frequencies with minimal distortion makes them essential in communication systems and wireless devices. Measurement instruments such as oscilloscopes and signal analyzers often use FETs in their input stages. The high input impedance of FETs prevents loading of the measured circuit, ensuring accurate readings. This property is crucial for precision measurement and scientific research. Audio equipment such as microphones, preamplifiers, and mixers often use FETs for their low noise and high fidelity. FETs help preserve the quality of audio signals, making them a popular choice in professional sound systems and recording studios. FETs are used in sensor circuits to amplify weak signals from sensors such as temperature, light, and pressure sensors. Their high input impedance ensures that the sensor's signal is not affected by the amplifier, resulting in accurate and reliable measurements. Communication systems, including radios, televisions, and mobile phones, rely on FETs for signal amplification and switching. The high speed and low noise of FETs ensure clear and reliable transmission of information, making them indispensable in modern communication technology. Summary: field effect transistors, including JFETs and MOSFETs, are vital components in modern electronics. Their unique construction, operation, and characteristics make them suitable for a wide range of applications, from amplification to switching. Understanding the differences between JFETs, MOSFETs, and BJTs, engineers and enthusiasts can design more efficient and reliable electronic circuits. As technology continues to advance, FETs will remain at the heart of innovation in electronics.